Hello friends. Hello.
Yes,
Yeah.
sir.
Yes, good evening. You have any questions on whatever I have taught so far? Hello? No questions. Right. Now that you have good clarity, so you see the current has to enter into the base, not from collector. The current can enter the base region either from the emitter end or from the base end. Okay, all right. And whatever current enters there, majority of the current is pulled by the collector. I hope that is clear to you. Now you see we are going into the next level, so you must have the clarity. What I just now told, if you have imagined, then I will be very happy. So you see this is the base region, this is the emitter region, this is the collector region. Now what I just mentioned here was now the current can be injected here or it can be injected here. Got it? You can inject the emitter current or you can inject the base current. Okay, right? And this junction, okay, is forward biased, and this junction is reverse biased. Under that condition, whatever current comes here, this current, majority of this current will go here, and only some current will go here, right? If you are pumping it from here. If you are pumping it from here, again the same thing. Majority of the current will go here, some current will go here. I suppose this idea is clear to all of you?
Yes, sir.
If it is not clear, I will clarify it.
Yes, sir.
That is how you have to look at this currents.
Sir, when the current is entering from base side, the current from that collector will come towards the emitter.
No. That's what I am going to tell you. See, this is reverse biased, man. This is reverse biased. Okay, see now try to understand. Whether the current is going like this, okay, or the current is going like this, right? So it's only the direction which is changing. I mean, if you look at it like that, only the direction is changing. Okay? Now listen here carefully. The junction is forward biased. So if the junction is forward biased, if the junction is forward biased, how should you look at the current? Okay, the majority carriers will go from here to here. That is the current. Part of this current will enter here, part of it will go here. Now, whatever part is entering here, that if I say is the main current, then this bifurcation takes place. It is only that you are looking it like this or you are looking it like this. It should not make any difference. Correct? That's how you have to understand. We are going into the circuitry level. Now, I hope this diagram is clear to all of you, right? And this convention is also clear to all of you. Okay? I hope this convention is clear. We should not confuse it. So instead of writing this arrow, I wrote this arrow in the exam, sir. Confusion, sir. No. No confusion. Just understand. The emitter based section is forward biased, and they are showing the arrow in the direction in which the current will flow. So if the current has to flow in this, and if the emitter based junction is forward biased, this has to be P and this has to be N. Correct? Okay, and obviously this has to be N. And if the current is entering like this, then this has to be P, this has to be N, and obviously this has to be P. Correct? That is the way to look at it. I am not teaching students, to heavily depend upon your memory and all. Everything in science is structured very well. You have to follow the structure and understand it. Right. And in the last class, I will have discussed this. And very important, the transistor will operate in active region, cutoff region, saturation region, and inverse active region. Okay. I will explain all these things clearly to all of you in this session. Now, emitter size is medium, very high doping, base smallest size, low doping, collector largest size, medium doping. Now here I'll tell you how to remember this, because in examination, sir, we got confused. Definitely, if you try to by heart, you are going to get confused. Okay. Now, what is very important is the current from the emitter has to go into the base, and the majority charges have to travel from emitter to base, and the majority charges from base to emitter should be negligible. I hope you remember this.
Yes, sir.
See, the name emitter itself tells that it is the source or emitting the current. Emitting the current in the sense it's not that it is like a fountain it is coming out, but you try to understand it. Therefore, that has to be highly doped. That has to be highly doped. Got it? And next the base has to be low, very low doping. I hope this should not be a confusion. Okay?
Yes.
See, I am waiting for response. You are wasting my time and your time. Keep your mic unmuted. I hope you got this. What is this, man? See, did I not explain this? See, you have to see my video before you come to my class. See, I told you no. This majority charges will flow here, and my other charges will flow. But see, now supposing this is N and P and N. So this is electrons, correct? And these are holes. So therefore, the conventional current, since electrons are flowing, the conventional current is in this direction. Now this conventional current I will have two components, IE and IH. But here you see this IH is very, very negligible. So for all practical purpose, this is IE. And why do we do that? Because holes, if the holes are more here, then there will be recombination here. So here what happens is the holes are few in number, so most of the holes are going to get recombined. So we want only majority charges to come here so that the next action will take place. If it was not for it, then this action would not have taken place. See, for that only I have spent almost 1 hour. Okay, Adil, see my videos, you must have a grasp of it before you come to my class. Okay, intensive study is necessary. So I hope there is no confusion between these two. And obviously the third will be medium doping. Understood? See, I am helping you people, students. See, you are going to write a final examination which will have 30 chapters of physics on a D-day. And 30 chapters of chemistry, 30 chapters of mathematics. See, in your college and all, they give you chapter-wise test, chapter-wise revision. Chapter-wise test, chapter-wise revision, you can remember. Because today you studied this chapter, tomorrow the test is there on that. But when you wholesomely learn everything and write an examination, well, if you are dependent upon memory, God save you. So therefore, science is structured. I am trying to give you that. So you observe it like that. Don't be, don't do like what you used to do in your middle school, by heart and then reproduce. Right. I suppose you understood this. Coming to size. See, now the collector-based junction is reverse biased. Got it?
Yes, sir.
And there is a large voltage. There is a large voltage between the collector-based junction, and the current is also quite high. Therefore, it has to dissipate a large amount of heat, and to dissipate a large amount of heat, the size should be big. Therefore, the collector region has got the largest size. Okay?
Yes,
And the emitter region has to emit a lot of majority charges. Therefore, you see the size is large, then you can have large amount of majority charges. Therefore, it is medium. And this is only, base is only acting like a support, okay, for the current controlled device to come into picture. And therefore, it is small in size. See, this is how you have to remember. You have to imagine, you have to understand the process, and then only you can remember. Anyways, I have explained this, and once again I have explained this. Okay, so working of PNP, NPN transistor, I have explained this in detail, and IE is equal to IB plus IC. How that has come into picture, I have told you. So 95% of the majority charges that go from the emitter to the base, they will go to the collector. Okay, that also I have explained to you. Now here now we are going to look at it from see now this one you can see the configuration how it is written here, current and now henceforth we are not going to use this. Okay, we are using this all to explain how the transistor works, and henceforth we are going to use the circuit symbol and write start learning about the transistor or start using the transistor. I suppose this diagram should tell you henceforth I am going to use the transistor symbol like this and continue my journey. Okay? Hello.
Yes, sir.
Okay. Now, before I proceed further, now I will tell you something. Now try to understand this very carefully. So, I am going to write the transistor like this. Okay. Now, what is this terminal? Collector. This is base and this is emitter. Correct?
Yes.
Now, I am going to make this the reference point. See, when I do like this, it becomes the reference point. That means I am going to reference this with respect to this. I am going to reference this with respect to this. Correct?
Yes.
Now, you see. So what happened here?
There is potential difference.
सब जोर मारो तेरी साइड पर.
So there is some potential difference created.
So you say there is VBE created. Got it? That's what you are telling? Hello?
Yes.
No, you have to analyze. You see, I have to teach you amplifiers. I have to teach you oscillators. And you have got very high level questions. So if you are struggling to answer at this level, God save you at the higher level. So aram se everybody there, not only him, analyze. What happens when you connect like this? He is telling there is some potential difference. That's all. What else will be there? What else? What are the other things that happen?
There will be some current flow.
You should tell all that. No, you want to waste your time and my time. When I connect this, what happens? You should tell. Sir, current starts flowing. There will be positive. There will be VB voltage, and there will be some current that will be entering here. I will call it as IB. Correct? Then here also there will be some current flowing.
Yes, some part of.
How much current will flow here? So I will call this current as IE.
Yes.
Now what is the relation between IE and IB?
So I should be equal to IB.
Good boy. That is how. You see, I want that confidence. And you can answer like that. Very good. In this case, because collector is open circuit, the current cannot flow there. Obvious. Very good. Excellent. Excellent. If you are understanding correctly, then you can answer like this. And this is how the questions will be asked, whether you have understood all these things. Well said. Well said. Good. Now, I am going to reverse bias this junction. Correct? So, I am going to reverse bias this junction. So, I am going to reverse bias this junction. What should I do to reverse bias this junction? What should I do?
Apply potential.
See, you are speaking to me. You cannot simply say apply potential difference. In what way should I apply the potential difference? You clarify it properly. See, you should tell man, you have to reverse bias this, no. You have to reverse bias this, no. So what will you do? See, this is what now here. this is Pn, isn't it? So this has to be N. So if you want to reverse bias it, so you are going to connect the positive plate of the battery to this. Correct? Now you should tell like that. That is important. See why I am stressing all these things is because students, you just take it for granted. Anyway, you connect this, you connect plus plate or negative plate, चलता है. उसका ऐसा attitude रख के सीखा है. I mean, if you learn, God save you. So I want you to be very specific. Okay, I will call this as VCC, and then I am going to connect one more resistor here, RC, or it is also called as RB sometimes, and then I am going to ground. I hope things are clear. Now, what current will flow here? Here, IC will flow. Correct? Hello?
Yes, sir.
Now, what is the relation between IB, IE and IC?
IE equal to IB plus AC.
IE is equal to IB plus IC. Good. Now, I taught you some alpha, beta and all. In terms of that, can you say? So, this is going to be what? Beta times IB. Correct?
Yes, sir.
And therefore, what is this current IE? No, now don't use alpha. If you are using beta, don't use alpha. So, this is obviously these two currents. This will be IB plus beta times IB. See, both the currents are going to flow here. Correct now? So, this I can beautifully write it as 1 plus beta.
1 minus.
Why?
So correct.
No, yes, so, no. Good. Nice, you have got it out. Now, understood now? See, I have written the direction of the current like this. So, therefore, I am writing it like this. So, follow this, correct? See, you should, just not going by books. They wrote minus, there I will also write y minus. Then, you see what I have written is correct. If you ask y minus, then you know it is correct. So, I suppose you understood all the configuration, everything here. Okay?
One dot,
Please.
sir, what is the role of that VCC and VBB type? Do they have any significance?
This is meant to reverse bias this junction.
Sir, but like their value will have.
That all I'll discuss. That all we'll discuss. That is what, I have to teach you the designing part. The value and all I will explain. How much should be that value and all, we'll discuss that. It's a much involved thing. See, we at engineering college, we have studied only transistor for full 1 semester. Almost half the semester. But I am supposed to teach you within 2 or 3 sessions. Okay, it's a tremendous pressure on you and me. I will teach you. Don't worry. That's a good question. I'll explain. Don't worry. You are inquisitive about it. I am very happy. I will teach you. Don't worry. Okay. Now you all have to have this. Get this clarity, right? Okay. Now you see. Before I bias this. Okay. So this is one issue. Now before I bias this, okay. So what is that? I'm going to write something, and you just have to apply your brain and understand. Now you see so now here you see these are the charges. Which charges? The charges here that has to flow to this point. The charges here that has to flow to this point, right? So that means now you see, now try to look at the depletion layer and things like that. The depletion layer between the emitter region and the base region. Can you imagine that depletion layer?
Yes, sir.
Now, which of the charges can overcome the depletion region and enter the it can overcome the depletion layer? Means which are those charges which from the emitter can go into the base section?
Majority charges, electrons.
Good. And all the majority charges can go?
Only electrons, not holes.
Correct. Majority charges only will go. But that majority charges should have some other property.
So like majority charges, most of them will go towards.
Which of those charges, majority charges, qualify to go into the base region. Potential energy barrier, those charges which have got energy to overcome the potential energy barrier, only they can go, correct?
We can go to collector.
Now listen here very carefully. See, now, you have to get connected to everything that I have taught before. See, now the moment you have forward bias this, okay, you have forward bias this, right? Before you forward bias, there is a depletion laser, correct?
Yes.
Now, after you forward bias, there are plenty of majority charges here, plenty of majority charges. But these majority charges cannot go from here to here unless they have energy to overcome the potential energy barrier, correct or?
Yes, yes.
That is what I wanted. So these charges cannot simply jump from here to here. Only those charges which have got energy to overcome the potential energy barrier, only they can jump. Got it?
Yes.
Now connect. See, it's all a beautiful theory. You have to get connected to everything. So look at the characteristics. The characteristic of ID versus VD is something like this, correct? And this is the cutting voltage. Okay. See, till this point, the transistor, the depletion laser is there, etc., and you are still in the non-linear region. And only after it reaches this point, we say that the transistor is on. Or for all practical purpose, you can take this to be linear. Got it? So now you want majority of the charges, majority of the most of the majority charges to come to this point. That means now, see, most of the majority charges here have already got energy up to this level, assume it. And now, you can make some of them to jump. Okay. What I am trying to tell you is, you see now, please listen very carefully. Now you are 100 students are there. Now you have to climb a wall. 100 students are there, you have to climb a wall. Say you are all some 5 feet or say 6 feet, you are all there. The wall is something like around 8 feet. Okay, 8 feet wall and you are 6 feet, 6 feet and the wall is something like around 8.5 feet or something. Now you want to climb the wall. Okay, there are 100 of you. So can you climb the wall and go that side? Yeah, some of you are energetic, so what you will do? You will run, come and jump. So you are 6 feet, say hand stretch, it will be 7 feet, and slightly if you jump, that 8 feet wall you can hold by your hand and then do like this and jump, correct?
Yes.
Can you imagine that? Others are keeping quiet here, what nonsense here. If you are in my live classes here, I would want to come and slap you, each one of you. Why don't you learn, man? Come on, answer. Say yes, no, something like that. Don't sit dumb there, you are sitting, you have to put effort and learn. If you are in front of me, I would have made you to learn. Each one of you. Right. At least now think that I am in front of you in your home and I am capable of, giving you one. Right. Sorry, but, I want everybody to learn and that's why, I am encouraging every one of you to participate. It's not difficult. Can you not imagine just jumping the wall? Right? Okay. So some of you can manage to cling on to the 8 feet wall and jump the other side. But not all of you. Correct?
Yes.
Now, there are 100 students. I want almost say 80 or 90 students to jump the wall. So what should I do? You are all 6 feet.
It should help them.
How will I help you? Correct, tell me. Good. Excellent. How will I help you? So you see, somebody else will come, they will put you on your shoulders and push you up so that they will elevate you by another 2 feet, then each one of you cling on and you can jump. Correct now? वही होता है. ये जो फॉरवर्ड बायस जो देते हैं ना हम, वो क्या करता है? देखो पहला, first of all, this majority charge here has to jump, has to have so much energy to jump, the potential energy barrier so much. Now, when I add this biasing, I am elevating this level. That means now the effort that has to be put by the charges is only so much. The potential energy barrier has been reduced by this much, or the potential energy, this is biased. What we call it as biasing, forward biasing, so that you are giving energy to all the majority charges. So much energy is there. Correct? Good. Right. Now, by reverse biasing this junction, what are you going to do? You are going to do like this. See, that means now those of the majority charges which are able to jump to this potential energy barrier level and come here will start swimming. And now you see, because of this reverse bias, there is a potential well. See, you are creating a potential well. See, this is, if you say, see, if you take this as a reference line, you have elevated here. And what did you do here? You have created a well, so that you jump there, you jump the wall, go a few places, then you are going to go down because there is a well there. Correct? And what happens? What happens to these charges? See, they manage to come here, but when they come here, they have to fall down like this. So you see, what is current? Rate at which the charge is moving. Correct?
Yes.
So here you see these charges will gain energy. So therefore, you know, these charges are capable of moving with higher energies. See, here the charges are moving with some energy, but here as they keep coming down this well, their kinetic energies will keep increasing, and therefore the speed will keep increasing, and therefore their energies keep increasing. And that is why they are able to overcome what? The reverse bias or the RR or the resistance between the collector phase junction. Got it now, all of you? The concept? Huh?
Sir, sir, if there is a well created cell, then like they will prefer to go towards that side of the business, why towards the base region, like that, base current.
Base current what? Okay. So this is good. So this is collector current. Right? This is collector. Very good. See, you are a good boy. See, just keep asking like this. You will really learn very well, and you will help me to teach very well. I should be thankful to you for asking questions. And I wish everybody, take a cue from him and ask. Now, see, the other day I explained to you, here you see, if I connect a battery to this, okay, so what did I tell you? Here, see, the hole is going here. So how many holes will be here? Say 1 million holes. Hello?
Yes, yes.
And how many electrons here? 3 electrons. 1 million free electrons. Fine. But now, say all these 1 million electrons will come here. Then what happens? Will the conduction stop? It will not stop. In fact, the majority charges will flow unless it is replenished here. This battery is sending the electrons. Correct now?
Yes, yes.
Same thing here, the electrons are coming out. Once the electrons comes out, the holes are created. Got it? So there is a continuous supply of holes here and electrons, therefore it is continuous. Got it?
Yes, yes.
Now, good. Here, in the case of transistor, the majority charges are coming here, okay, and large chunk of this majority charges are going here. Some of this is not able to go. Correct? What happened to those charges which are not able to go? They are, why they did not go? Because they recombined. There is recombination taking place here. Got it? Now, recombination is taking place, and recombination has to take place continuously. That means now, say electrons are, say here, from here, say holes are coming. So if the holes are coming, some of the holes have to disappear because the most of the holes will go here, but some of them have to be joined. That means there should be continuous supply of electrons from here.
Yes.
So the base current that is flowing there is basically what? It is the current to replenish to help the recombination or to ensure that recombination takes place. If this current is not there, the recombination will stop. Then the transistor action will stop. Did you get it? Did you get it? So therefore here whatever current is flowing in the base is because of the recombination. Those which will not recombine will go as collector current. And their energies will increase because it is entering the potential well. Is that clear to all of you?
Yes.
See, this is how beautifully the transistor built. See, this is an engineering miracle. And today you are getting this world, so, stick, mobile, that, this, everything is because somebody invented this. If this was not invented, you see how the world would have been. Just imagine. And this is the beginning of something that we are engineering. We are building technology. And you are going to learn a lot of engineering and technology in the near future. Fascinating things. And this is the beginning of a long story, okay, that all of you are going to enjoy for the rest of your life. Okay, I hope I made all these things clear to all of you.
Yes.
So, this voltage, forward biasing voltage, is going to flip or push this here, and this is what we call it as biasing. Forward biasing, and we are going to pull the valve here down, and this is because of the reverse bias. And this is how the transistor action takes place. Have I made myself clear? Hello?
Yes, sir.
Right, good. Okay, so from here on, I will take you to the forward channel. Okay? Alright. It's very exciting, very exciting. Now, what shall I do? I have to preserve some of this. Right. Okay, let's preserve it here. Might need it later. Okay, now this is one part of the story. So it's so biasing. So therefore, you see, we have to make the transistor ready for operation. जैसे कि आपने व्हीकल को स्टार्ट करके चालू करते हो, बाद में गियर डालते हो, एक्सेलरेटर दबाते हो, कार चलना शुरू करता है कि नहीं? और ट्रैफिक सिग्नल, when it comes to traffic signal, you are idling. That is, your vehicle is ready to move. Its only thing is, well, you have to accelerate. You have to put the gears. Correct? No? Same way. Now, by biasing, you have made the transistor ready for operation. That is precisely what you have done. Okay? Now you see, whatever current is flowing, this IB, what I am showing is IB, IE, and this IC, all capital letters, what I am writing here. IE is equal to IB plus IC. All these currents are biasing currents. They are all biasing currents. They are just currents flowing, the voltage is across, and they have made the transistor ready. Got it? Okay, now you see, let's look at it like this. So if you look at the input of the transistor, which is this is the input. So this is IB versus VBE. IB versus VBE. IB versus VBE, the graph is going to be like this. Okay? Hello? And now I am going to write here VCE. What is VCE? Voltage between the collector and emitter. Hello?
Yes.
Yes.
VCE is the voltage between the collector and emitter. This is VCE. Symbol you understood?
Yes.
Voltage of the collector with respect to emitter. That is the thing. Okay. Now, by biasing here, what have I done? That means now when I bias here, my VBE is somewhere here and my IV is somewhere here. Got it? Understood? So the intersection of these two. So this becomes what? The operating point. That means the transistor is now at this point. VBE is here, this is, and IV is here. So I have fixed the operating point of the transistor. Correct?
Okay.
Don't by heart, don't simply say yes, involve yourself. Come on, grow up. See, all of you are very lucky. I am teaching you. A person from IISc, M.Tech in electronics is teaching you. When I was a student, well, I did not have this luxury at all. And I am very enthusiastic to teach you. You are all wonderful students. So just involve yourself and learn bharpur. God bless you. Okay, so here I am going to write IC. Okay, and here I am going to write VCE. Here I am going to write IC and VCE. Another graph I am creating. So how will this graph look? BC. Okay, aram se. Now aram se understand this. So what is VCE? VCE will be equal to, see, I am going to write an equation here. That is, I am going to write an equation. VCC minus ICRC will be equal to VCE. Do you agree? See, if you start from here, okay, so there will be, the current is flowing like this. There will be drop across this. Hello. So this drop is minus ICRC. And there is rise of potential here, plus VCC. Okay, and what is that? That is nothing but equal to this voltage. VCE with respect to VCE. Agree?
Yes, sir.
Everybody, come on, this is the basic equation, nothing to by heart here.
Yes, sir.
Right, good. Now I am writing this, I can also write this, like this. How? VCC minus beta times IB RC. Correct?
Yes, sir.
So that means now I am passing a particular IB. What is this IB I am passing here? Let it be IB1. IB1. So IB1. So for some IB1 I am passing. So for some IB1, I am getting some IC. I am getting some. So for some IB1, I am getting corresponding IC1. Got it? If I put IB is equal to IB1, then it will be equal to IC1. IC1 is equal to beta times IB1. Got it?
Yes.
And at that point, what will be the voltage between these two? It will be VCE1. IB is equal to IB1, then IC is equal to IC1, and VCE will be equal to what? VCE1. Got it? So say VCE1 is somewhere here. VCE1 is somewhere here. So what happens? The intersection of these two points. This is one. Okay?
Yes, sir. Yes, sir. Yes, sir.
Aram. Okay. So I have got IB here, so. Okay. Now you see. Now aram se understand. Now supposing I will vary RC. You can see here RC.
Yes, sir.
Now, if I vary RC, what will happen?
So VC will either increase or decrease depends on.
Brilliant answer. Brilliant. VC will either increase or decrease depending upon depending upon the value of RC. Excellent. Well said. So that means now if I go on increasing RC, this point will keep going up. Got it?
If we yes, it will go this side.
It will go this side. Okay. It will decrease, it will go that side. Correct. If you decrease, it will go that side. Correct. And if you decrease, it will go this side. Correct. Okay. Right. It will go this side. It will increase that side. It will go that side. This will go this side. Correct. Well said. Correct. Brilliant. See, you follow me. Huh? See, whatever I say is not the truth. What you understand is the truth. I am trying to tell as much truth as possible. But sometimes slip of tongue, I may go wrong. But that doesn't mean you have to understand it the wrong way. So if you are also alert, then definitely, even if I miss out something, you will be able to learn correctly. Very good. That alertness and awareness is something which is very important. Well said. Now, you see the situation. If I go on reducing RC, the point will shift to the right. But will it change IC? Will this line be flat line? Or will IC also change if I change RC?
IC will be constant.
Why?
So because it will only depend on IB.
Array, wow, such a good boy. Yes, IC will not depend upon anything except IB.
Yes, sir.
As long as IB is constant, IC is constant. Correct? Okay? So this current will not vary. This current will vary only if this varies. But if this varies, this will not know. Because this is dependent on this. Okay? Right. Well said. Well said. Well said. Very good. So now one is, if I decrease RC, the graph, the points will get here. But if I increase RC, the points will keep coming to the left. Correct? So will it go on coming to the left and come to this point? It will not come to that point. Why it will not come at that? Now aram se. Now look at this equation. If I go on increasing RC, then what happens? What happens? This voltage will start decreasing, So if I increase RC, this voltage will start decreasing now.
Yes.
So now assume that I have given VBB as something like 5 volts. I have given VBB as 5 volts. This voltage at this point should be less than 5 volts. Then only this is reverse biased. Correct now?
Yes.
No.
Yes.
See, this voltage has to be more than this voltage. Then only this section is reverse biased. Got it? VCE must be greater than VCE must be greater than VB. Then only this is reverse biased. Correct now? Reverse bias, man. See, for reverse biasing, this voltage with respect to this must be greater than this voltage with respect to this.
Yes, yes.
Only Arun is telling yes sir, yes sir. What about others? देखो जी, reverse biasing क्या है? See, this voltage has to be more than this voltage. Then only this is reverse bias. If this voltage is more than this voltage, then this is forward biased. Correct? No. See, for this to be forward biased, this should be more than this. No. And for this to be reverse biased, this should be less than this. No. This should be less than this. No. Or this should be more than this. No. See, if this is 5 volts, then if you say, assuming that some drop is there here, 5 volts minus the drop here is VB. So what is VB? VB means VB with respect to emitter. Emitter is grounded. Will be what? VBB minus IB RB. Got it now? Hello?
Yes.
Okay. Supposing this is 5 volts. Okay. And RB is say 1K. RB is 1K. This is 5 volts. Okay. And I will say that IB is 1 milliampere. Okay. Then 1 milliampere into 1K will be equal to only 1 volt. 5 volts minus 1 volt will be 4 volts. So this will be 4 volts, correct?
Yes.
Now, so this voltage has to be greater than 4 volts, correct now?
Yes, sir.
Then only it is reverse biased.
That's it.
Now you see, as you go on increasing RC, VC will go on decreasing. Say this point is say something like around 4 volts. Now, if VCE becomes less than 4 volts, then this transistor, this is not reverse biased. This is also forward biased, this is also forward biased. Got it?
Yes.
Then this, so you can expect this graph to be a straight line here, but once it comes here, you cannot expect the graph to be a straight line.
Yes.
Got it? You can't expect it to be a straight line. Why? Because the moment this voltage becomes less than 4 volts, then the transistor action will stop. This junction will simply act like a forward bias junction. This will also act like a diode. This will also act like a diode. So if this is now this voltage is this voltage VB and this voltage is VE. So VB is greater than VE. This is forward biased. So the current will flow like this. Okay. Now VC, if VC becomes, this is VC, and if VC becomes less than or equal to VB, then this is also forward bias. Then the current will flow like this one. The transistor action stops.
Yes, sir.
Understood? The transistor operation will stop. Okay. So what happens? The base current will simply get divided into two parts. The collector current will no longer be the collector current. So therefore, this graph is going to be like this. Do you understand?
Sir.
Understood? So this is
that I1 IC, sir, it will not even depend on VC or VCC or something.
See, now listen here. Now don't look at it like that. Now look at it from this point of view. Now don't go to VCC. Please don't go to VCC, because here you see you have to look at this voltage here. VCC is there, but there is also current that is flowing here. See, this is not like an ordinary electrical circuit. Here it is a transistor, active device is there. See, in electrical circuit, we are dealing with passive components. Resistor, capacitor, that are all passive components. But here you are dealing with an active component. So things are going to be different. So, did you understand the formation of this graph? And this is for IB1.
Correct.
Got it? Now, if I increase IB1 to IB2, if I increase IB1 to IB2, either by increasing VBB or decreasing RB, then what happens? I will get another graph like this, and the same thing will happen. This is IB2, and similarly I go on increasing, I will get VB. Got it? Hello?
Yes, sir.
Hello,
So
all
you
of
are changing RC with respect to the SS.
I changed RC and this. Now I am changing IB and I am showing you the different curves.
Yes, sir, correct.
So therefore now you see this becomes what? The output characteristics. This is output characteristics. This becomes what? Input characteristics. Output characteristics and input characteristics. Got it? Okay. So this corresponds to IC2. This corresponds to IC3, and so on and so forth. So on and so forth. Okay. So on and so forth. Okay. So that is how you have to keep understanding the things about the transistor. Okay, so this is how you get the output characteristics, and this is how you get the input characteristics. Okay, so now you see this part. So this region, see in this region, that is this region. See, in this region, what you have to see, if you increase IB to IB, if say now IB1 is flowing, current is IC1. Now, current becomes IB2, IC2 increases. Current becomes IC3, IB3, current increases. Understood? So here you see, as IB is increasing, IC is also increasing. Got it? As IB is increasing, IC is increasing. That means in this zone, IC will be equal to beta times IB. Got it?
Okay.
But in this zone, IC is not equal to beta times IB. Got it?
Correct.
Yes.
So this zone is useful for us because what we want amplification. Right? See, you remember the other day I told you amplification AV will be equal to what? Beta times RL divided by RB. Of course, if you take this RF into consideration, you have to write RF, but RF is very small, so all practical purpose, the voltage gain will be equal to beta times RL by RB. Got it?
Yes.
Provided the transistor is in active region. See, this formula holds good, provided you are operating within this zone. Then only you will have voltage. Okay?
What will beta depend upon?
Good question. That is a good question. That will depend upon how you manufacture the transistor. How you manufacture the transistor means what is the size of the transistor, what is the doping concentration, what is the area, all that put together, you will be able to create the transistor for the required specification. There are many specifications. One of the important specifications is beta. So you will learn in higher classes. If I want to make a transistor of so much beta, then what should be the concentration gradient, etc., etc. So you will create. You are the creator of the transistor of any beta.
Yes.
Any other question? Clear? Hello? Right. So this is the output characteristics and this is the input characteristics. Okay? Clear?
Yes, sir.
So now again I am going to draw the same circuit, but this time you see. So I am going to draw RVP. I am going to draw this, and I am going to draw this. And I am going to draw the transistor. So this is V in, this is V out. Got it? Enjoy, man. Don't be afraid of life. Just enjoy. Okay. Right? Now you are all good students. So you will tell me what is VO equal to. See, there are two things now here. Hello. Now, see, you are all wonderful students. Come on. There are two currents that are flowing here. What are the two currents that are flowing here? One is because of this source, another is because of this source. But see, that is voltage source. Voltage source will do its job irrespective of what other voltage sources there are. Got it now? That's it. So you will have two currents here. What are the two currents? One is IB and the other one is IE. Correct? And here also, what are the two currents that will flow here? One is IC and the other one will be what? Also, for IN, you are going to have corresponding IO. Okay, corresponding IO for IO. Got it? Now I am going to use a word called signal. What is a signal? You know what is a signal?
Convey.
Correct. A physical variation that will convey information. Right? Now supposing I'll say like this. That means you know what I mean? I'm telling you to stand up. And supposing I do like this. What do I mean? Sit down. Got it now?
Yes, sir.
So a variation which contains information is called signal. Correct? So if I do like this, you will get up. If I do like this, you will sit down. Correct now?
Yes, sir.
If I do like this, what will you do? You don't know what to do. It doesn't contain any valid information. Got it now?
Yes, sir.
So that is why this is a signal, this is a signal, this is not a signal. Understood? Now, so this Vn is indeed voltage source. Okay, voltage source. But here, this I am going to consider as a signal source. I can consider it like this because I will say that it has got information. Okay, yeah, it has got information, so I will consider it as a signal. Got it?
Yes, sir.
So this is, I will consider as signal source. Signal source. So it contains signal. So now, what is that I want to amplify? I want to amplify the signal. See, I am going to sing a song here. Okay, assume that I am singing a song. Right? Shall I sing a song? Okay. Usually in the class, I used to sing, but you are all keeping quiet. I don't know. I am amused. I don't know. Assume that I am going to sing a song. And what do you want at the output here? You want my song to amplify. Supposing I sing here, I am singing it my normal voice. Okay. Na ha da de, I said. But now in the loudspeaker, the same song, same tone, same Sudheer Murthy will be in an amplified form. I suppose you understood what I meant.
Yes, sir.
So if I want to write it here, the signal source, say the signal will be like this. And the amplification, what I am going to get here, the amplification I am going to get here will be, but it will be much less. I am showing the phase inversion. Understood? So this is VO, this is V. Okay, right. So therefore, this one contains information and this one contains information. Understood? This is not going to contain any information. That is only there to bias the transistor.
Yes.
Is it clear? Is it clear to all of you? So therefore now, when I say the voltage amplification AV is equal to beta times RL by RB. Okay, see, I am just considering RB here, I have neglected this resistance here and all. There are ways of doing it. Or, in other words, if you see from V in, what is the impedance that it sees? That is, the impedance that this voltage source is going to see, because this voltage source has to send current against this resistance and against this resistance. Okay, so if I put both those resistance together, then I can write it as RL divided by RI. RI matlab input resistance. The resistance seen by this voltage source to push the current into the transistor. Okay, right? Hello?
Yes, sir.
So this becomes this. Now what you have to notice here is, well, the voltage gain will depend upon the output load resistance, the beta of the transistor, and also the input resistance. It will depend upon all these three factors. And what is AV? AV is delta VO divided by delta V. It is voltage gain. Got it?
Yes.
Somebody is having doubt to ask, I will explain.
How do you get the delta?
What is EV, man? See, you have totally these 3 days. I sent the video in the morning so that you'll read. You have totally forgotten these 3 days. I didn't take class. You have forgotten everything. You have forgotten. See, I explained in the last class now what is delta VO. What is delta VO? See, this current will see if this current changes, if this current changes to delta IO, then there is a corresponding change here, no? Delta IO. So this delta IO into RL. That is what is this output voltage. Right? Okay, got it? Right. It's okay. Okay, still if you want, I will derive it for you, not an issue. At least you are having doubt and you are asking, but your great friends sitting there. So this will be RL. And what is delta V in here? So delta V in will be delta I in into R. Okay. And what is delta IO? Delta IO will be beta times delta IO into RL divided by delta I in into RL. So delta I in, so you get this. Okay? So this is how the transistor will work as an amplifier. Clear?
Yes, sir.
You have any question you ask? I'll aram say.
Yes, sir.
Because you are going to solve many difficult sums on this. This is trivial. This is nothing great. I am teaching you. Now again I am going to draw the same circuit. Okay. This time you see there is something like this. I hope you understood what is this. What is this? This is a switch. Hello. Hello.
Yes, sir.
This is a switch.
Yes.
So I can connect it here, or I can throw it and connect it here. So this can make a connection like this, or this can make a connection like this. Okay. So this is one point. So this switch, either I will connect it here or here. So if I connect it here, it is grounded. But if I connect it here, it is connected to VB. Got it?
Yes, sir.
Yes, sir.
Good. And this, as usual, I am grounding. And this one again here. Now watch out here. This one again here. I am going to. So what type of transistor is this? NPN transistor. Correct? So this one I am going to connect like this. Okay. Now that this switch is this is connected to this point, ground point. So what is VO equal to? So in this case, see, when I have connected this switch to this point is grounded. What is Vin equal to and what is VO equal to?
Vn is 0.
Good. And what is VO?
So that circuit is open.
Give me the answer. So only one student wants to sit and learn in my class. Others don't want to learn anything. Only he is trying to answer. Come on, everybody give an answer. What is VO? See, Now, if you look at the transistor from this side, how will it look? It look like how?
If there's some current I flows, minus I VO. Sir, if there's some current flows, I, then
See now.
VO will be
See,
minus I.
listen here. From here I see. So what is the resistance between this point to this point? What is the resistance?
Even R backward step R.
See now what is the configuration? This is emitter, base, correct? No. So what is that I have done? I have grounded this. This is also grounded, and here to this I have connected this like this. Correct? No. Hello.
Yes.
So now under this circumstance, you see here, say now here I am using a NPN transistor. So this junction is reverse biased. Hello.
Yes.
So what is the resistance here? Between this point and this point, what is the resistance? That is this resistance. Yeah. RR no.
Yes, yes.
And RR now is very large compared to R. Correct?
Correct.
Now I am asking you what is the voltage at this point. So for all practical purpose, if you consider this current equal to 0, because this resistance is very large, man, only reverse bias current is flowing, it is in microamperes, you can neglect it. So then what will be this voltage? VC, isn't it? Yes or no? Because this voltage, if you apply the loop here, how much? See, now you see here, try to understand. Now here this is 0, okay? This is, see, now understand, be careful. See, now you say this voltage is, see, this voltage is 0, okay? Correct? Now no current is flowing here, okay? So no current is flowing, that means there is no drop across this resistor. Correct? Then no current is flowing here, but this point is at what? This point is at what? This point is at PCC. This point is at PCC. This point is at PCC. Okay, so this point is at PCC. This point is at ground. Okay? So now Kirchhoff voltage law has to be satisfied. Kirchhoff voltage law has to be satisfied now. Hello? So if you write the loop equation, here, for the loop equation, then you will get V naught will be equal to VCC. Correct? So for V in equal to 0, V naught will be equal to VCC. In now. Huh?
Only VCC, no, sir. That VCC will be across that RR.
See. So this point is VC. Okay, this point is E. We have wrote the equation VCE is equal to VCC minus IC into RC. We wrote like this now. Hello. Now here you see this IC into RC is what? Now RL. Okay, IC into RL. So this will be VC is equal to IC into RL. Okay. So go from this equation and tell me. So in this case, IC is equal to 0. IC is equal to 0. So VCE will be equal to VCC. Correct?
Yes.
VCE is equal to VCC.
Yes, sir.
So therefore it should be 0, isn't it? V naught must be equal to 0.
V naught should be
ठीक है? Okay. ठीक है? Great. Now I just slightly change this. I'll just slightly change this. I will now take the output here, V0. I'll take the output here, V0. Okay? I'll take the output here, V0. Now what will be the value of V0? Now it is VCC. Correct? Clear?
That's it.
Good. See, I wanted you to get the difference. Okay, so I wanted everybody to apply your mind. So therefore, I created this writing here. So if I take the output here, then if I take the output there, then V0 is equal to VCC. Right? Hello?
Yes, sir.
Now I will take this switch. And okay, now I'll connect the switch here. So if I connect the switch here, then Vin will be equal to what? Vin will be equal to VB. Correct? Okay, I'll say VB. Correct? Now VO will be equal to what?
Sir, VCC minus IC.
VCC minus?
IC current.
Good. VCC minus IC into R. Okay, excellent. So VCC minus this one. Now here I would like to draw your attention here. So what is that? So now you look at the output characteristics. IC versus VC. Okay, so here you see you are going to get the characteristics like this. Correct? Hello? Now here you see in the first case when you had connected this to this, IB was equal to 0. That means somewhere here in this zone. You are operating in this one. Correct? You are operating in this zone. Now here you see when you connect this to VB. Right? And now you see the corresponding current IC is flowing in this circuit like this. Okay? So this voltage now is what? This voltage now is less than this voltage. You told this V0 is equal to 0, no? So if this voltage becomes less than this, this is also forward biased and this is also forward biased. Correct? Hello?
In which case are you talking about?
In this case, and second case, when you close the switch here, this voltage is V0 is equal to 0, no?
No, sir, not 0.
It will be some small voltage. You want to take some small voltage?
If you take small voltage, yes, sir, correct.
If you take some small voltage, okay. And that is approximately equal to 0. Got it? Approximately equal. Will you agree approximately equal to 0? Okay, done. So if it is approximately equal to 0, then it is going to operate in this zone. Agreed? It is somewhere going to operate in this zone. Right? So somewhere going to operate in this zone, and the current is now, a lot of current is flowing. This current is now, see, now here IC is not dependent upon IB. Got it now? IC is dependent upon IB only in the active region. In this region, it is not. Okay? So therefore, now you understand this. See, now you see. Now this zone. Which zone? This zone. In this zone, no base current is flowing, no collector current is flowing. So this region is called cutoff region. This region, yellow region. Got it? Because no base current, no collector current. Negligible base current, negligible current, it is for all practical purpose 0. Correct? Now, when you connect this to this, current is flowing here, but this is forward biased and this is also forward biased. Now, the transistor is operating in this zone. Got it? And this is called saturation zone. Saturation zone. Saturation region. Understood?
Okay, yes.
And now this region is called active region. This region is called active region. Correct? So active region, saturation region, and cutoff region. Did you identify these three?
Yes.
ये उड़दोर माताड़ लो, हाँ,
So the cutoff region, sir.
हाँ,
Say, like, for if for a small value of IB on this, RB also, sir, that is one value of IC must.
see, when I'm putting the switch here, what is the base current that is flowing? Zero, no?
Yes, sir.
Zero base current is flowing. So this region is also reverse biased. Hello?
So I see and I see.
This region is reverse biased. No base current is flowing. No collector current is flowing.
No, sir, when IB equal to 0, IC equal to 0.
IC equal to 0.
So then that region will not exist.
That region will not
Exist. Sir.
good question. Good question. That region will not exist. So therefore, below this IB is equal to 0 region, whatever is that region is called cutoff region. Below IB is equal to 0, see this region where I am marked in yellow neatly here, no?
Yes, sir.
So you are telling, sir, there are no characteristics there. Why are you telling like that? That's what you are trying to tell.
So but according to that graph, sir, when IB equal to 0, there will be some corresponding value of IC, no, sir. According to that graph.
See, it is not like okay. I got your point. See now, see here. If IB is equal to 0 here, obviously there is no current flowing here, and therefore the transistor is not working. Correct. Now the thing is like this. The thing is like this. See, I have marked. See, now somewhere I have to mark a zone and tell you below this it is 0 and all those things. No, somewhere I have to mark it. No. So I am marking it here, and that's it. That's it. Somewhere I have to mark and tell you. So that is why I am marking. So below that it is cutoff region. That's what I want to tell you.
Yes,
Okay, and this zone is saturation region. This is active region. Got it?
yes, sir.
Okay. So if you have understood these three regions, very important, because you are going to have interesting questions on this region and on this what I have talked about. Okay. Okay. Shall I continue? I have to continue, whether you say yes or no. Okay. Shall I move on?
Yes, sir.
Now you see. Now what I am going to do? I am going to connect a small bulb here. Assume that I am going to connect a small bulb. When will this bulb glow? See, this bulb is nothing but resistor. When will this bulb glow?
And there is some value of IC, sir.
Some current, whatever rated current flows, then the bulb will flow. Correct now?
Yes, sir.
So here you see, when I connect it to this point, when I connect this to this point, which point? This point. Okay, then so V in is equal to 0, and what will happen to the bulb? The bulb will
Not in
yes, is off. Correct? Now, when I connect this to this point, okay, when I connect it to this point, see now here what I am going to do. I am also going to connect this to not VBB, I can also connect it to VCC. That is, I can take this voltage and this voltage C. Correct? So in this case, what happens? Now V in is equal to VCC, and what happens to the bulb? The bulb is on. Correct? Bulb.
That will be in saturation.
Correct, man, it is in saturation. That's what I want.
Correct.
So now you see, now here it is in cutoff. Agreed?
Yes, sir.
Here it is in saturation.
Okay.
Okay, now understand this very carefully. Understand this very carefully. Okay, so I have used BCC like this and I have written down things like this. Okay, okay. Now, what you have to now understand is this switch I am going to use. This switch will operate with small currents. Small currents in milliamperes. Okay, say 1 milliampere, 2 milliampere. But for this bulb to glow, you want at least 1 ampere current. So 1 ampere is 1000 milliamperes. So you see, I can have a small switch which operates in milliamperes, and I can ensure that current of 1 ampere flows in the bulb. ठीक है ना? That means एक small switch से मैं बड़ा current control कर सकता हूँ. अभी transistor is operating in what? Transistor is operating in cutoff and saturation region. So now I say the transistor is acting like a switch, on-off switch. The transistor is working like a on-off switch. Now at this stage you understand like this. At this stage you understand like this. So you are thinking, sir, ये क्या है sir? अभी ये switch you are doing tuck tuck. Say same thing I can do tuck tuck and close and open this bulb. That's what you are thinking, right? So why do I note this? It is not like that. Huh? See now here you see, I will have a small IC. So I will have a small IC. Say the name of the IC is 555 timer. So for this, you give some voltage VCC and ground. So this one at the output here, this will generate small pulses like this. This will generate small. This will work like oscillator and start giving you pulses like this. Can you understand this? Hello.
What is that, sir?
Small, see this IC called as 555 timer. At this point, when you give VCC and ground to this IC will generate this type of a voltage.
Okay.
Understood? It is generating this type of a voltage. And this VCC is say 5 volts, and this is grounded. And for this bulb to go, I need a voltage. See, this voltage I am giving here is 5 volts for this IC, and for this I am giving here VCC equal to something like around 10 volts. Sorry, something like around 30 volts, and I am sending a current of approximately 1 ampere. Okay, so now you see, if I connect this timer to this, then this bulb, what happens to this bulb? See, for this bulb will now become on and off, on and off, on and off. Understood? So you are all running light system and all disco light and what you see, it is all like this. Because see now this for 1 ampere current to become on and off low, then the manufacturing the switches they like that, and doing it in hand and all is difficult. So here I simply connect on IC here and leave it off, and I can change this frequency. I can make this frequency large and frequency small. Frequency large, the light will go on dig like this. If I make the frequency less, tuck, it will do like this. Okay, there are many uses of this. I will explain all those things later on. But now what I want you to understand is the transistor will work between cutoff and saturation region, and the transistor is working in the switch mode. Okay, and if you bias the transistor, base emitter region, forward bias, collector region, base bias, then it will work in active region, and in an active region you can use the transistor as an amplifier. But in cutoff and saturation you cannot use it in amplifier. Only in that you can use it as amplifier. Got it? Understood? So this is very important thing that I have taught you today. Okay? So transistor as a switch, transistor as an amplifier.
In saturation region, sir. What will IC depend upon, sir?
That is the beauty. IC will not depend upon IB.
Yes, sir.
Correct. IC will not depend upon IB. Agreed?
Sir.
IC will depend upon VCC and RC. correct? IC will depend upon VCC and RC. Why? See, saturation का मतलब क्या है? Saturation का मतलब क्या है? Saturation का मतलब है अभी you cannot control. वो गया, it has reached its saturation point. You cannot now control. That is called as saturation. The collector current cannot be controlled by the base current. Then we say it is gone into the saturation mode. वो सुनता नहीं बा, वो पानी ऊपर से गया, all the dialogue we tell, no, like that. Okay, I have explained the major part of the transistor to all of you. Done. So basic transistor configuration. Now here you see there is common base configuration, common emitter configuration, common collector configuration. So here you see here I can see here. So what I have now shown is, so this emitter is, see, this emitter is, so far what we have discussed is the emitter is the common point. The common point between input and output. So this is called common emitter configuration. Now there can be configurations like this also. So here what happens? This is called common base configuration. So your input is here, output here. Then you can have configuration like this. So you can have input here and you can have output. Collector is this, common collector, common base. So each will have its own advantages and disadvantages. That is not there for your syllabus. Only know that there is common base, common emitter, common collector configuration, and widely used is this. So common emitter characteristic is what I have now explained to all of you. And experimentally you have to conduct this experiment and then get those graphs. What I have shown. Okay?
Yes.
So input characteristics I have already explained to you.
Yes,
So this is say VC is equal to 0, VC is equal to 5 volts. So I have already told you the graph is going to shift to the right as we increase the VCC. If you increase the VCC, the graph is going to shift. The input characteristic is going to shift. Okay? Right. Output characteristic also I have explained to all of you. ठीक है? And transistor is an amplifier. This circuit also I have drawn and I have explained to you. ठीक है?
Yes.
Now, just for comparison, so common base, common emitter, common collector configuration. These three diagrams I have just now drawn and explained to you. Clear? Hello? Now I will just for this one, if at all, see, I am teaching you at a slightly higher level so that questions can see every year. The question paper standard will keep on increasing. So just to make sure that you can answer the question slightly above a particular level, I am just explaining this. There is nothing to by heart. Okay. Now input resistance. See, input resistance means if you connect the input here. See, if you connect the input here, okay. So this voltage source has to push the current. So it has to push it means it has to see some resistance here, right? So the input resistance for this configuration, it will only see a diode. So the resistance is low. Correct? Hello. Okay. This is okay. Okay, I'll explain this tomorrow to all of you. It is already 9 o'clock. I don't want to tax you further. I'll explain this tomorrow to all of you. Fine, students?